Okay, and we'll now do the PowerPoint from current slide. Well, there we go. Well, okay, here we go. Now, where we are, what we're going to be doing, we're going to finish Chapter 8 now. Then we'll have the lab on Chapter 8. That's all that's required to be done today. Okay, if any of you want to come back tomorrow or Thursday, anytime, I'll be here all day long, both days, to do your Chapter 8 test and or the final exam. That's up to you. Okay, if you want to take it at the end of the day, that's fine with me too. Okay, but you won't have had much time to do this last part, but that's up to you.
You said you're going to be here tomorrow, right?
I'll be here tomorrow from 7:45 in the morning approximately until 5:15 in the evening approximately.
If I came over here like 11:30ish?
Yes, I should be here. Now, you know where my office is? You know where my office is? Okay. If I'm not in my office, check all the classrooms between my office and here, because if anyone comes in to make up a final or something else, then I'll be in whatever classroom we can find closest to my office. It's empty. So look there. Okay? Now, any questions before we get started today? All right, now what we did up till now was talk about the quantum numbers, the quantum, the way the electrons are numbered, named, placed, and that determines what we call the electron configuration. Remember, Pauli's exclusion principle said no two electrons will have exactly the same set of quantum numbers. And they have two that are n's are the same, two that the l's are the same, two or more that the p's are the same. But and then of course there could be some with spins the same, but never will any single electron have all of those quantum numbers exactly the same. I think we maybe talked about that last time, didn't we? I think we did this slide. And the chemical properties are determined by the electronic structure. Okay? So again, the arrangements of the electrons basically defines how the elements are placed in the periodic table. Excuse me. Okay. And quantum number 1, the principal quantum number, n, equal 1, 2, 3, 4, 5, 6, or 7. Those are the rows in the periodic table. Excuse me. Okay, those are the rows in the periodic table. The angular momentum quantum numbers determines partially what columns they're in. Not totally, but what columns. The S electrons are in the first two columns. The elements with the first two electrons, the S electrons filling up first two columns. Then the P electrons are the ones over here to the right, those 6 columns. Then the D electrons are these 10 columns in the middle here. And then the F electrons are in the 14 columns at the bottom. Okay? So that's your angular momentum quantum numbers. The magnetic quantum numbers basically are defining what the orientation of those angular momentum quantum numbers are. And then the spin quantum number is just spin up or spin down. And that's the final thing that distinguishes the others. That determines the atom's quantum state, those unique set of numbers. That's Pauli's exclusion principle. Each electron has a unique quantum numbers. Now, do electrons care? Not really, okay, but they do have those, the way we classify them. The maximum of 2 electrons per orbital, one spin up and one spin down. So they can't, 2 of them have the same thing. And in any other, they have, in one given orbital, your N's the same, your L's, L's the same, your magnetic quantum numbers are the same. Just spin up, spin down will be up. The chemical properties are determined by electronic structure as well. Everything in the first column here, remember that was with your angular momentum quantum number S1, the first electron in that. These are very active metals, light, soft metals, lithium, sodium, potassium, rubidium, cesium, and francium. Now, the last two you don't see that much, but those are very reactive. They have just one single S1 electron in their outer shell. Really easy for them to lose that, and they form very strong electronic bonds. So that's what it means. The chemical properties are determined by that electronic structure. The S2s, when they fill those form pretty strong. There are two positive charges. If they lose both of those, they become two positive charges. They form strong electrostatic bonds. Okay, electronic bonds. Okay. The next over here, these are shared electrons a lot. So you form really strong covalent bonds there. Of course, the column 8, filled outer shell, completely full, they don't combine with anything. That's why they call them the noble gases. They do not combine with anything. So you see, the chemical properties are determined by those electron structures. Okay? These metals there, the D electrons, they don't tend to stay in one particular place. Those are your clouds of electrons that your metals. These are your transition metals. These are your good conductors of heat and good conductors of electricity. And the way they bond, all that is determined by those D electrons. These down here, very rare, very heavy. No one really knows. Well, I guess somebody does that studies them, but you just don't run into those very much. But their chemical properties are based on this electron configuration. Now, how do these shells get filled up? So the electrons, when you're writing these, the electrons fill available orbitals in increasing energy. And the energies don't quite follow the same way you probably would expect them to. And that's why the periodic table has those little dips and dives in them. Okay? And we'll talk about that. The shell capacities. The S shell can only hold 2 electrons, the S1 and the S2. The P shell can hold up to 6 electrons. Okay? P1 through P6. D shell, up to 10 electrons. Those are the transition metals in the middle. Okay? And the F shell can hold up to 14 electrons. Those are the rare earths, the lanthanide and the attenanide series at the bottom. Okay, they're going to show you strontium. Okay? I don't know if any of you are all familiar with strontium. I'm not. But here it is, number 38. It's in the 5th row, 2nd column. Okay? Strontium has 38 electrons, which means it has 38 protons. How can you tell the number of neutrons? Oh, it was a long time ago, at least 4 days. How can you tell the number of neutrons? 38 is called what? The atomic number. There's another number associated with strontium on the periodic table. What's that called? Atomic mass. Okay? For strontium, it's, can hardly read it, almost 88. So what would that tell you? Help me. Subtract 38 from 88, and that gives you 50 neutrons, exactly. Okay? Because the protons and electrons for a neutral atom have to be equal. The rest of that mass is basically neutrons. Now, why is it a fraction? It's actually 87.6. Why is it 0.6? Strontium can have some atoms with 50 neutrons, but others only have 49 neutrons. do we call those? An atom with, of course, the same number of protons and electrons, but different number of neutrons. What is that called? Oh, a long time ago. Well, I can't find it. There it is. Nope, not quite. Here it is. Last word on the slide. Last word on the slide. Isotopes. If two atoms, of course, if they have the same number of protons, it's the same thing. Strontium, 38. Okay? But if one has 50 neutrons, the other has 49 neutrons, those form two different isotopes of strontium. Okay? Iso means the same. They're the same element, but different number of neutrons. Because you can have different number of neutrons. Okay. So let's get back to all right, we're close. All right. So we're going to do strontium. Here's how we do it. The first thing you do is write down all the possibilities. In the first row, you can only have s electrons. Okay? How many? 2. Okay? Second row, you have s electrons and p electrons. How many s? 2. How many p? 6. Okay? Here's how you tell that, folks. Think of s as 1, double it. P is, go to the next odd number, 3, double it. D, next odd number, 1, 3, 5, double it. 10. Next odd number, 7, double it. 14. That's how you can tell how many, the maximum number of electrons you can have in that shell. Okay? So in the second shell, you can have s electrons, 2 of those, and up to 6 p electrons. Third level, this is n equal 3. You can have s, p, or d electrons. Okay? How many s's? 2. P's? 6. D's? 10. All right. It's easy, but it takes a while. Okay? In the fourth shell, you can have s electrons. How many? 2. P's? 6. D's? 10. And F's? 14. Exactly.
So it goes up 4 every time.
What's that?
So it goes up 4 every time.
Yeah. Okay. If you just went 2, 6, 10, 14. You can remember it that way. Okay. In the fifth shell, now you would think there'd be another one out here. We run out of elements before we get to the next one. So we're going to stop at F's. So the fifth will be S, P's, D's, and F's. 6 will be S, P's, D's, and F's. The seventh will be S, P's, D's, and we don't even get to the F's. We've run out of elements. Now maybe somewhere out there in the universe there's some more elements, and if there are, you might go a little further. But I don't think so, at least not in our solar system here. Now, you might say, what are these arrows here for? The arrows show how these shells fill. And to begin with, it's just like you would expect. But let's do strontium. Strontium is what? What's its atomic number? 38. So let's start. It's going to first fill. Let me get my pen activated. It's first going to fill the 1s, and how many electrons are that? 2. And then it goes back to the top and does the 2s. And how many is that? 2 more, you're up to 4. Then it goes back to the top and does the 2p's. How many is that? 6. So you got 4 and 6 is 10 so far. 3s. How many s?
2.
So that's up to 12. Then you go up to the top again. 3p. How many there? 6. 4. Okay, what's that up to? 18. 4s.
2.
Which is 20. Okay. Now we go up again. Now we go back to the 3D. So notice here, folks, we filled 1s, 2s, 2p, 3s, 3p, 4s, but we did 4s before we did 3d. That's because the energy, the electrons in 3d are actually a little bit higher energy than 4s. So they start here, then they go back up here. How many in D? 10. Okay. You don't have to go back and keep count. Then 4p. Okay, let's do it. 2, 4, and 6 is 10, 12, and 6 is 18, 20. 10 would be 30. 6 more would be 36. 38. Stop right there. And guess where you're on the periodic table? You're on the 5th, n equal 5, 5th row, 2nd entry. 5s2. You stop there. That's strontium. You see how that works? And you can just keep going. You always go to the bottom of the arrow, go to the top of the next arrow, bottom to the top, bottom to the top. And you see we really don't even have any 6Fs either, okay, that we filled up yet. Because if you notice, those Fs are the rows at the bottom, and by the time we get down there, you're up to the lanthanide and actinide series, and that's all, folks. We don't have anything past 103. Well, no, I'm sorry. We do have past 103. That would be 104 over here. It picks up the, after the 5F, you do the 6D, and then the stuff, we don't even do, and 7P. Sorry about that. Oh, I'm sorry. No. Yeah, 6D. That ends it for us. If we needed to do more, we do 7P, but there, no, I'm sorry, we do 7P, but we don't go to 6F. There's no 6F down here. Or actually there is. Well, it's a little confusing here. The lanthanide series is filling row 6, but it's 4F electrons, okay? And then the actinide series is filling row 7, but it's in the 5F electrons, okay? As you see, you start with these two before you do any of those, okay? And that's why the gap is here. You do those series next. So you see how you fill these shells? And guess what, folks? You'll be doing this on the lab today. So understand it. Follow it. Okay. So strontium is 1s2. Here's how you write them. 1s, 2 means 2 electrons, 1 spin up and 1 spin down. 2s, 2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Just like we did as we call it. And you keep count of how many electrons you got. When you reach that number, stop. Make sense? And that's why the periodic table looks the way it does. Has hydrogen and helium at the top. Those are the 1s, only 2. Then 2p, you have 2 over here, 6 over there. Then 3s, 3 and 3p, 2 and 6. Then you do 4s. Then you go back and pick up the 3ds. That's why it stretches out there for another 10 in there. Then you do the 4p and the 5s, and then you go back and get, so you keep filling in that manner, and that's where they fall into place. Okay, your fireworks configuration, that's what strontium is used for. Okay, certain strontium, atomic number 36 chemicals are used to add the pure red color to the flares and fireworks. So you probably have used or seen or watched strontium and never knew it. Okay, that little blurb there at the top. The figure 18.6 does a little bit neater what I was doing here. It shows the path that the arrows take. All right, any questions on that? So let's look at how those chemical properties are related to the quantum numbers. Understood in terms of electron configurations, the electron in the outer orbits determine the chemical properties. These are summarized in the periodic table, and it's really remarkable. The guy who put this together was a Russian guy named Mendeleev, and he just did it based on the chemical properties, not knowing beans about electron structure. Later, when the quantum mechanics people figured out quantum structure, it fit his table almost perfectly. Okay? The rows are called the periods. Okay? That's why we call it periodic table. Those are the primary energy levels. The columns are the families or groups. And that very first one that I mentioned to you before, and by the way, it has a name, column 1A, and those are your alkali metals. Now, they usually put hydrogen here. Hydrogen is not a metal, but they got to put it somewhere, so sometimes they'll put it over here, but it really doesn't go over there either. Hydrogen and helium don't sort of fit as well, okay? Number 2A is alkaline earths. They're like the alkalis metals, but they're alkaline earth metals, you might say. Way over here in 7, these are the ones that have 7 electrons in their outer shell. They want 8. They grab electrons like crazy, become strong negative ions, and then they attract the positive ions from the column 1A. That would be like sodium chloride, salt. Okay? Lots of salts are made that way. Something from alkaline earth combining with the halogens. 7A are called the halogens. 8A are the noble gases. Okay? Now, the A group families, these are the 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. These are basically the S and P electrons. The main group are representative elements. Now, what the number means for you is how many electrons are in the outer shell. 1, 2, 3, 4, 5, 6, 7, and 8. 8 is a perfect number for an atom. It doesn't want any more. That's why the noble gases don't combine with anything. 7A, they have 7. They want that one more. They'll rip off an electron from somewhere over here and then form a strong electrostatic bond. Okay? The alkali earths will sometimes give up 2 electrons and they form strong electrostatic bonds. The ones in here, 3, 4, 5, and 6, tend to form covalent bonds. Rather than gaining or losing that many electrons, they share electrons. Okay? So, now the B group, those are the transition elements or metals, and those are your D electrons. A lot of those are free electrons. They travel in packs. They're clouds of electrons. You don't usually talk about that many, but typically the number above those, and it's rather strange the numbering here, 1B and 2B are over here next to the D electrons, and then 3B, 4B, they're right next to your 1, 2A. So it's 1A, 2A, 3B, 4B, 5B, 6B, 7B, 8B, 9B, 10B, and then you pick up 1B, 2B, 3A, 3B. So The numbers make sense. It's just that they don't see. Now, in general, now this isn't absolutely true, but that's how many typically free electrons are in your outer shell. Okay? Not always the case, but it's typically. For the transition metals, is how many are usually out there free to just float along wherever they want to. Transition elements are transition metals. Most of the time, metals. Okay? So that number that precedes A or B, that tells you generally how many electrons are in the outer shell. Generally. Okay. So here's your periodic table. These are your periods, 1, 2, 3, 4, 5, 6, and 7. Your columns represent the families or groups. I couldn't remember what they call it. The 1A family, alkalis, metals. 2A family, alkaline earths. All the B's are transition metals, but the numbering of 2A, 3B, 4B, 5B, 6B, 7B. Now these three are put together 8B. In your book, back of your book, I'm sorry, I said them wrong. I said 8, I was reading them. These are all 8Bs, okay? Because 8 is about what fills an outer shell, and these all have 8. Where the rest of them go, not real sure, but 8 electrons in the outer shell. Then 1B, 2B here. By the way, just for general purposes, does anyone remember our best conductor? Very best conductor.
Silver.
Silver. Look where it is. 1B. Next best conductor.
Gold.
And
Copper.
copper. 1B. Next. Gold. 1B. So only one electron there. Real easy for that to move around with almost no line loss. Very little resistance to the motion of those. The further on you get, these are usually not great conductors here. Okay? So all that varies. Aluminum is close to that. It's a fair conductor, a pretty good conductor. Okay? So you can't quite piece everything together there, but just to point out to you, there are 3 of your best conductors right there. Copper, silver, and gold. Silver, copper, gold. Okay. All 1Bs. So lots of information is given here. Okay, and again, tell me, pick an element, any element there.
Cobalt.
Cobalt. There it is. What's its atomic number?
27.
27. What's its atomic mass?
58.
Actually, round that up to 59. Okay, how many protons are in cobalt? 27. How many electrons in cobalt?
59.
27. No, number of protons has equal number of electrons, otherwise it's not neutral. Okay? How many neutrons are in cobalt?
27.
No. The difference between 59 and 27. That would be 32. 32 neutrons most of the time. Every now and then you'll find a cobalt with only 31. Okay, and that's why it's a round off number there. Okay? But it's pretty close. There are not many that are beyond that. Okay. Good deal. Any questions on that? And all right. They show some of these electron structures, and they do show you a shorthand for it. Okay? You can use this if you know what you're talking about with it. Cobalt. Let's give its electronic structure. Now what you could do is start at the beginning, 1s1, 1s2. So you just do 1s2. 2s1, 2s2, so you do 2s2. 2p, how many? 6. 3, what letter? S, 3S, how many? 2. 3 S, P, D, L. I don't know. Come up with something to remember that. 3 P, how many? 6, okay? Second? 4S, 2. And then, for cobalt, 3, if you go back to this, okay, you did 1S, 2S, 2P, 3S, 3P, 4S, 3D, that's where you are now, 3D. But to get to cobalt, it's 3D, 1, 2, 3, 4, 5, 6, 7. Stop at 7. Cobalt would be 3D7. The maximum you can get is the 10. You don't have to do that. Only if you're going down to here would you get all 10 of those, or somewhere else. Somewhere below that you would get all 10. Does that make sense? Now here's the shorthand. Go to the noble gas just before you got there. What's the last noble gas you get to before you get to cobalt? Argon. Argon 18. You can just do argon 18, then you do 4S2, 3, D, 1, 2, 3, 4, 5, 6, 7. And you do it. So that's why they have that shorthand abbreviation at the top there. Now, they have a misprint on that. For helium, on lithium, they have a helium with a superscript 1. That superscript 1 should not be there, okay? Let's see, I don't think these are on the slide set. No, they're not, okay? So forget that one, but then you 2S1 and you stop. You're right there at helium, okay? So they don't put the total numbers before. I thought they did, but they don't. So that's the shorthand way of listing these, so you don't have to list them all. But you can list them all. It's perfectly fine to list them all. All right. There is a periodic practice there under concept applied. You might want to look at that and play around with it. All right. 8.6, metals, nonmetals, and semiconductors. Okay, remember, what's in column 8? 1A? 8A? What do we call those? Far right column of your periodic table. Noble gases. They're inert. They do not combine with anything. So those are noble gases, filled shells, inert. They will not combine with anything. That's why they're gases. Even with an atomic mass of 222, still a gas. No gases are that heavy except for noble gases. Okay. Now, when you have 1, 2, or 3 outer electrons, you tend to lose those really easily. That would be your 1As, alkali metals, 2As, alkaline earths, and even the 3Bs will tend to lose electrons pretty easily, becoming positive ions. Go over to the 1B, 2B, but especially the 3As, aluminum and those also will lose electrons fairly easily. Those are your metals. 1As and 2As are soft metals. You wouldn't think of them as metals, but they are. But all the Bs and the 3As are pretty strong metals. Okay? When you have 5 to 7 electrons, okay, that's over there in the 5A, 6A, 7A, they tend to gain electrons and form negative ions. Okay? Those are nonmetals. And then you have things called semiconductors that are in between the metals and the nonmetals. Usually the nonmetals are non-conductors, and the metals are usually good conductors, or nonmetals. In between those are your semiconductors, and here's how we picture those. Okay, now they're giving you another configuration, way to express your configurations. This is called the dot notation, electron dot notation. Hydrogen just has that one electron and one dot. Helium, 2 electrons, but that's a filled outer shell. It's not 8, it's 2, because S can only hold 2. So it's a noble gas. Lithium has whatever helium was plus 1 outer electron. Beryllium, whatever helium was plus 2 outer electrons. Jump over to boron, helium plus 3 electrons, carbon is helium plus 4, and then they start pairing up. As long as you have single electrons, they stay single. But when you get more than 4, they start pairing up. So carbon will combine with 4 other materials. Nitrogen with 3, oxygen with 2, fluorine with 1. You see, fluorine loves to rip off an electron from some of these, and then they form strong ionic bonds. Once you fill the shells, they don't combine with anything. So that's your noble gases, all having a filled outer shell. 8 electrons, except helium only has 2. Everything in column 1A, 1 spare electron, so they tend to form positive 1 plus 1 ions. 2A tends to form 2 plus ions. 3A tends to form 3 plus ions. 4s, they tend to form covalent bonds. They share electrons, they don't lose or gain them. Nitrogen tends to either pick up 3 or do covalent bonds. Oxygen likes to pick up 2, fluorine picks up 1 and forms ionic bonds. So you see where they land in the families, that tells you what kind of electronic structure. The electronic structure tells you what kind of chemical properties they have. Now let's look at the semiconductors. Here we go. So everything here, the 1As and the 2As, and all the transition metals, this is the metal side of things. Okay? Over here, noble gases are all gases. Your non-conductors, okay, are over here. Now, some of these are gases, some are not. Fluorine is usually a gas. Chlorine is usually a gas, okay? Bromine, I think, is usually a solid. Iodine, I think, is a liquid, but it's either liquid or solid, okay? Oxygen's a gas. Nitrogen's a gas. These others are solids at normal temperatures and pressures, but they're non-conductors. They're non-metals. These green ones are your non-metals. These are noble gases. These yellow ones in here, the border between the metals and the non-metals, these are your semiconductors. Boron, silicon, okay, that's where Silicon Valley, semiconductors, they form that. Germanium and, I can't remember what that is, actinide or something like that. No, arsenic, I'm sorry, arsenic, semiconductor, okay? This is tin and that's antimony, I think. Strange. Tellurium and, that may be antimony. Yeah, antimony, and then the other one down there is astatine. Okay, these are your semiconductors, non-metals, metals, noble gases. So that's the other way these are split up. Everything over here tends to be a metal. Now, some of the metals are liquid. One, mercury, strange, but it is true. All the rest of them are solids at normal temperatures and pressures. The non-metals, some can be gases, some can be solids. Maybe 1 or 2 liquids in there at normal temperatures and pressure. Your semiconductors are a little bit metal-like, but also non-metal-like, so they're semiconductors. Okay. In your book, they're purple, green semiconductors, and sort of tan for your non-metals. And in the book, they list the noble gases as non-metals too. Okay. Any questions on that? All right. That, folks, was your last slide. Okay. It's not the last thing in the chapter. There is a closer look at your rare earths. Now, the rare earths are those that show up in these two rows down here at the bottom. Those are the alpha electrons. You got 14 of those. They're very rare, but very valuable for especially things like electronics and things like this. A really sad situation. Probably the biggest concentration of a lot of these very rare minerals is in Central Africa, especially the Congo. Because they were, okay, the Congo specifically was colonized by Belgium. And Belgium ripped them to shreds. They were probably the worst of the imperial countries. They treated them worse than dirt. And they just raped the countries. And the country could not benefit. Now, it's the Chinese. Okay, they're not colonizers, but they go in and they buy up things. They buy it up real cheap, but the Congolese think they're getting a real good deal, and then the Chinese take over. Everybody's competing for those things, but the Chinese have really gotten in there. That's why, in many ways, their battery technology and other things have really passed most of us. Yes.
Is Silicon Valley called Silicon Valley because of the element?
Because of the semiconductor industry. Yeah, that's where it got its name. Is from the silicon was one of the early semiconductors, and they did a lot of things with it. Now it's still used some, but they've gotten to some of the more esoteric ones, that they can do even better things with. But that's where it got its name. You're absolutely right. Okay. Then I mentioned him already, Dmitry Ivanovich Mendeleev, 1834 to 1907. Now he was Russian, but what does those dates tell you? Communist Russia? Soviet Union Russia? No. What I'm saying is he wasn't that. He was the Tsarist Russian. Back when, Nikolai, I can't remember the names of it. Huh? No, way before that. Huh? The Tsar, the Russian Tsar. That sort of the end of them. They took over, they lost in 1914. So just 7 years after his death, that Russia, Imperial Russia, disappeared and became Communist Russia. So he was not a Communist Russian, he was an Imperial Russian. Okay. Closer look, semiconductors, top of page 224. That's well worth a read. And the metals and the charges, that's a pretty good little blurb there. And the illustration there at the bottom of lithium losing an electron and fluorine gaining an electron to make lithium fluoride, pretty good read there too. Other concepts applied, outer orbitals, they tell you a little bit more than what we've just said, so that's worth a read. And I think that's pretty much it. And as I say every time, nothing replaces reading the chapters. Hopefully you already have, especially if you're planning to take the test today. The summary here is a pretty full, long summary. It summarizes some stuff, but this chapter has more names and more concepts in it than just about any of the others. The summary of equations is not that long, only 5 of those. The key terms, a fairly good number, probably more than normal. And then applying the concepts, 49, that's probably a bit on the high side there too. They give the answers, good things. Hopefully you've already studied for them if you're planning to take the test today. Questions for thought, about a normal number, maybe a few fewer, but for further analysis, normal, maybe a little higher. The parallel exercises, the group A, you have those answers are in the back of the book. Group B are not. So you should be able to do a lot with those as well. Any questions? And that's all, folks, for the lecture today. I mean, the class time. You ready to start the lab?
Yes.
Okay. Well, what I'm going to do is pass out the labs to you. I may just pass out. Okay.
Are we doing it here?
Yeah, we're going to stay right here. It's just a paper lab, so we don't have to go anywhere. Okay? And it's basically this last stuff, the stuff we did last time and today on one. Johnny, can I get you to turn on the light?
Yes.
Okay. Take one past 2. Take one past 4. See if I gave you enough. One for Samuel. Anyone sitting here? Yeah, David here. And one for Helen. Okay. Anyone here? Yes, there was one. Andrew, that's one for him. And that is 2 for Chris and Melba.
It's a gaming.
That's 1 for Chris. And did we lose Hunter for good?
No, he'll be back.
Thought you were going to say if we lost Hunter, that would be for good. No, you wouldn't think that, would you? Okay. All right. Now, be sure you put your name. I had a class yesterday. Someone turned in some work with no name on it. I still haven't figured out whose it is. Last meeting of the class, how am I going to figure that out? I don't know. I'll work on it. All right, you have 4. Okay, so the following atoms, there's carbon, magnesium, iron, and gold. Okay? I've listed the 12 and 6, 24 and 12, 56, 26. What do those represent? The upper number, upper left, stands for?
Atomic number.
No, the lower left is the atomic number. The upper left is atomic mass. Very good. Okay? So for the following, identify the number of protons, the number of neutrons, and the number of electrons. There you have a space for each one of those. Okay? Identify whether it's a metal. Okay, I'm sorry, the electron configuration. Write the electron configuration. Now you can write it out fully, and again, I would use that chart that you see back there in figure 816 on page 219. That will be a good one to use, and you can also use the periodic table that's on the very next page. Okay, and you do it like they listed some there. Okay, electron configuration. List the period. You'll get that right off the periodic table. The family, right off the periodic table. By the way, the period is going to be a number, just a number. The family is going to be a Roman numeral followed by a letter. Okay? Metal, non-metal, or semiconductor. Flip over one more page, bottom of 223. And there you'll find your metal, non-metal, and semiconductor. That's figure 819. And then the number of outer orbital electrons. Remember what I said that usually was? Go back to your family, that Roman numeral. That's going to tell you in general about what your number of outer orbital
What was the
electrons.
family again?
What's that?
What was the family again?
The Joneses and the Smiths. Oh, I'm just kidding. Okay, that's the column title. Roman numeral with a letter, capital letter. It's on the periodic table. Okay? Any questions? And this is a lab, so you can work together or you can work separately. I think Benjamin Franklin said something about that, didn't he? All hang together, all hang separate. There's 2 more pieces of pizza. One. Off your road, bud. Oh, I'm sorry. The other one.
No, I didn't want it. Thank you, though. Yeah, I had a piece.
Should I have ordered a 6-piece, you think?
Oh, yeah.
I'm sorry. Y'all told me though.